So in this particular video, we have a system of 3 blocks that are actually going through elastic collisions in each one of these collisions. So if you need to pause the video, read the problem, and then keep up. All right, part A wants us to find the speed of M2 after the first collision. Part B wants us to find M3 after the second collision, and then it asks for all these little speed, kinetic energy, momentum for M3 after the collision compared to M1 in part C. Okay. All right. I'm just gonna go ahead and crack out part A. Part A wants us to find the speed of M2, so I'm just gonna set up conservation linear momentum. I highlighted elastic here just so it keeps you on track. One, in elastic collisions, momentum is conserved and also kinetic energy is conserved. So those are two important concepts to keep up as you follow along. Okay. I'm just gonna set up conservation linear momentum. One, there's only one object moving, that is M1 in the green. It has an initial velocity of 4 as stated in the problem, and then after it collides, it will have a momentum afterwards, and then block 2 is gonna obviously move forward in this case. So therefore, initially you only have one object moving. Hence, I only have on the left side is P1I. On the right hand side, I have two terms because M1 and M2 will have a velocity. I know that they do because in this particular problem, M1 and M2 are not the same mass, so therefore they will have two different velocities. All right. Other than that, I'm just gonna go ahead and break up P1I into M1V1I, and then P1F into M1V1F. Likewise with P2F, I want to break that into M2V2F. But you notice here I highlighted M2 because in the problem, the mass wasn't really given. However, it is given in terms of one and the other. For example, in this one, it's just that M2 is 2 times M1, whatever M1 is. So it's twice as massive, okay? So I'm just going to go ahead and do a quick substitution. Wherever M2 is, because I don't know what M2, I can substitute in for a true statement. In this case, this M2 is 2M1. So I'm just going to go ahead and get rid of M2. So I'm just going to carry the same exact line down. On the left side, nothing has changed. M1V1F hasn't changed either. Except instead of M2, I'm going to rewrite it as 2M1 because the problem says so. Okay. As you can see here, M1 will cancel out in each term because it appears in every term. You can cross that out. So it really reduces down to just a pretty basic statement here. V1I is given as 4 in the problem. Hopefully you paused the video and read it. V1F, I don't know what that is. And then here, only the M1 cancels out in this term. The 2 in front stays, and then V2F stays. So therefore, I have 4 equals V1F plus 2 V2F. But you notice here, this has two unknowns. So right away, just with experience, I'm just going to go ahead and isolate for V1F because this term is already by itself. So why not, okay? So to get V1F by itself, I want to go ahead and subtract both sides by 2 V2F. Hence, I move this to the left side, so that positive 2 V2F will become negative. So here I have 4 minus 2 V2F equals V1F. Alright, so you notice here I can't really solve this problem just using conservation linear momentum. So right away, I do have to set up my kinetic energy because in an elastic problem, as highlighted earlier, kinetic energy must be conserved. So here I'm just going to set up my statement for KEI and KEF. Initially, the only object moving is M1, so here I have 1/2 M1V1I square, and then afterwards I have two objects moving. In this case, I know they have two different velocities because these masses are not the same. If these masses were the same, the velocities would just switch, and that would be too easy for you to do. All right, other than that, I'm just going to go ahead and cancel the 1/2s out because it appears in every term. And then once again, I'm going to get rid of M2 and replace it with this true statement as given in the problem, as I did with linear momentum. M2 is 2M1, so hence instead of writing M2, I'm just going to substitute out M2 for 2M1. So M1 is going to cancel out just like it did with the conservation linear momentum concept. And here I'm just going to go ahead and simplify. 4 squared is 16. The only term left here on the right side is V1F square and then 2 V2F square. So that I'm going to carry everything down that I haven't canceled out yet. Excuse me. But here, hopefully, as you learn to identify, on the left side, using conservation linear momentum, I isolated for the variable that's already by itself, which is V1F. But I noticed here, in using conservation of kinetic energy, I have V1F square and 2 V2F square. So at this particular junction, I'm just going to go ahead and isolate for V1F square because I have a V1F by itself. So this is kind of just using common sense here. Okay, you want to solve for the term that's already by itself without complicating this particular algebra steps coming up. All right, so to get V1F squared by itself, I'm just going to go ahead and subtract 2 V2F squared and then that'll move to the left side of the equal sign, which will make it negative. So here I have 16 minus 2 v2f squared equals v1f squared. Well, this is v1f squared. On the left side, using conservation linear momentum, this is only v1f. So in order to get v1f to square, I'm just going to square both the left side and the right side. So I'm going to square the right side, which makes it v1f squared. However, squaring the left side will require you to multiply this term twice. So here I just wrote this term out twice. 4 minus 2v2f squared twice in parentheses. And here you just have to FOIL correctly. So hopefully your algebra skill is on point. If not, you do need to practice your FOILing skill. So here, 4 times 4 is 16. And then 4 times negative 2 will give you negative 8. But these are two identical terms, so that'll be negative 16. And then negative 2 times negative 2 will give you positive 4. Alright, so other than that, here's the 16, because 4 times 4 is 16. As I said earlier, 4 times negative 2vf will give you a negative 8 v2f, but then there are two terms identical, so that'll be negative 16 2vf, and then a negative 2 times a negative 2 will give you a positive 4, but v2f times v2f will give you v2f squared, and that equals to v1f squared. But now that you have two expressions for v1f squared, we're just going to go ahead and set these two statements equal. So watch one, I'm kind of circling back and forth with my cursor. So at the bottom left of the screen here, 16 minus 16 v2f plus 4 v2f squared, it's going to be equal to 16 minus 2 v2f squared, because they both equal to v1f squared. So as you can see here in my work, I have a 16 on the left, a 16 on the right, both are positive. That's going to cancel out. I need to set this whole function equal to 0 so I can use quadratic. Why? Because I have a v2f squared and a v2f. I think the easiest way to do is just to use quadratic solver. Okay. Other than that, this negative 2f squared will be moved to the left side, so that will become positive. But here I'm just going to combine like terms. I have a 4 v2f squared and a 2 v2f squared, and both these terms are positive, so I'm just going to combine like terms and make that a 6. The negative 16 v2f just gets carried down. 4 plus 2 is 6, and then the whole thing is equal to 0. At this point, you do whatever you want in order to get v2f, but I would encourage you to just use a quadratic function. And if you use a quadratic solver online or on your calculator, you should get two values of plus 2.667 or 0. And I'm going to go ahead and cross 0 out here because 0 cannot make any sense. Okay, it doesn't make any sense because m1 and m2 are different masses. The only way that m2 would come to a stop is if m1 and m2 were equal masses, but it's not. So therefore, I know by deduction that 0 cannot be an answer. So my final velocity for block 2 after the collision is a positive 2.667. It's going to move to the right at that rate. Okay, I mean, just using common sense here, v2f cannot be 0. It's kind of weird to have something strike something, but then have it stay still, which doesn't make any sense. All right. So I encourage you to use common sense once you get two answers using a quadratic solver. All right. Other than that, that is kind of it for part A. It wants us to find the speed of block M2. So I do want to point out, because it does ask for speed, you can simply say 2.667 without the positive sign here. Okay. I put the positive sign here because I initially solved for velocity, but I'm reading part A and it says find the speed. So the answer, if you're listening, would simply be 2.667 meters per second. All right, so leave the positive sign out. All right, let's go ahead and crack out part B and C. To do part B, it asks us what is the velocity of M3 after the second collision. So keep in mind for this one, I want to highlight again. It says that once M2 hits M3, it also goes through an elastic collision, so it doesn't stick together. So which means we just need to really do the same physics now using the new VF2 that we found in part A. So I'm just going to set up the really pretty much the same work here. Okay, initially, if I'm just looking at M2 and M3, the only object moving is M2. So after it got struck by M1, M2 will move to the right, but it's going to strike M3, which is initially at rest. And if M3 is initially at rest, it has no momentum initially. So on the left side, I only have a P2I. On the right side, I have a P2I plus a P3I. Once again, M2 and M3 are different masses, so the velocities will be different at the very end. So I know they'll be moving. And here it says M3 in the statement is M3, which is equal to 2M2. So keep that in mind as you follow along. So here I'm just going to use the same strategy here. I'm going to break up P2I into M2V2I, P2F into M2V2F, and then P3 into M3V3F. However, once again, I highlighted M3 because I don't know what M3 is, but the problem sets that M3 is indeed 2M1, excuse me, 2M2. So therefore, I'm just going to do that quick substitution. So instead of writing M3, I'll just write it for what it is, which is 2 times M2, whatever M2 is. So as you can see here, just similar like part A, M2 in this case, or 1, the masses will cancel out. In this case, it would be M2 because it appears in every term. So the only thing left is V2I, V2F, and then 2 times V3F. But V2I I already found using the previous answer in part A. We found that after the first collision, M2 will move to the right at a rate of 2.667. That's where that comes from. So this is the answer in part A. V2F I carry down because I don't know what it is. And then 2 times V3F gets carried down. So as you can see here, once again, we have this statement with 2 unknowns. If you understood the part A, here I have V2F already kind of by itself. So I'm really going to solve for V2F by moving this 2V3F to the left side, which would change signs. So here, I'm going to say that 2.667 minus 2 times V3F is equal to V2F. And then using conservation kinetic energy again, because it says elastic, I want to say KEI equals KEF, but KEI is now initially from M2, and then KEF is after the collision. Okay, so here I'm just going to leave the 1/2 out. If you watch part A, all the 1/2s cancel out in KE, so I'm just going to leave that out for this step, so it minimizes my step here. So here on the left side, it would just be M2 V2I square. On the right side, I know both objects will be moving at the end because they don't have the same mass. So because they don't have the same mass, they have different velocities at the end, which implies that they have different kinetic energies. All right, and that M2 V2F square, and then here I have M3 V3F square. Once again, the 1/2 has been canceled out visually if you kept up with part A. Here, I'm just going to substitute out. V2I was 2.667 from part A. I'm going to square that. And then here on the right side, I want to substitute out M3 because I don't know what M3 is, but I know that it's equal to 2 times M2. So it's twice as massive as M2. So I want to do that quick substitution as well. So as you can see here, M2s will cancel out. Therefore, I'm just going to square 2.667. That'll give me about 7.11. And then the only thing left on the left side here is V2F square, which I carry down. And then the 2 in front of V3F square gets carried down as well. So as you can see here, using the same strategy, I want to go ahead and isolate for V2F square because it's already kind of by itself. I want to move this positive 2 V3F square to the left side. And so therefore I have 7.11 minus 2 V3F square, which is equal to V2F square. Once again, I have a V2F square, but on the conservation linear momentum concept, I only have a V2F. It's not square yet. So I'm going to go ahead and square the right side. Squaring the right side will cost me to square the left side. So here, I'm just going to FOIL. I'm going to write 2.667 minus 2 V3F twice in parentheses. So I'm just going to FOIL. Hopefully you can FOIL correctly again. So if this is a skill that you need to practice, I definitely highly encourage you to practice how to FOIL. All right. Other than that, you should get 7.11 minus 10.668 V3F plus 4 V3F square, which is equal to V2F square. So I'm going to set both these functions equal. So once again, watch where I'm circling. 7.11 minus 2 V3F square, it represents V2F square, and then I have the same statement down here that represents V2F square as well. So I want to go ahead and set those two statements equal, just like last time. The if you recognize here, the 7.11 is on the left side, 7.11 is on the right side. So those two terms will cancel out, or you can just move and subtract. So it would be 7.11 minus 7.11, which will give you 0 anyways. So you can just visually cancel that out. And here I have minus 2 times V3F squared. I'm going to move that to the left side, which will make it positive. So I can set the whole function equal to 0. All right. So other than that, this is pretty light work. So the negative 10.668 V3F gets carried down because it hasn't been touched. And then these two terms are like terms, so we combine them, simplify it. 4 V3F squared plus 2 V3F squared equals 6 V3F squared. Once again, I would just use a quadratic solver. If you use quadratic solver, your A coefficient would be 6 because it's a positive 6. Your B, which is the term with just the variable by itself, would be negative 10.668. And then your C, I don't see a C, so C would just be 0. And if you do that properly on your quadratic solver or on your calculator or online, you should get two values of positive 1.778 or 0. Once again, if you heard my reasoning in part A, 0 for this one is kind of stupid. It doesn't make any sense because once M2 collides with M3, M3 has to move forward. It cannot be 0, okay? So 0 by deduction is just a dumb answer to go with. So even though you get two answers, you have to use common sense here. All right, so I'm going to say that V3F would be 1.778 meters per second. Okay, so that's the answer for part B. And you do need the positive sign in this one because part B asks for velocity, which is a vector. So the answer for part B would be positive 1.778 meters per second. All right, let's move on to C. Part C asks for you to make the statement, right? It says, are the speed, kinetic energy, and momentum of the block 3 greater than, less than, or the same as the initial values for M1? So you're looking to compare M3 and M1. Well, here for the speed, it's kind of stupid. You just found the speed for M3, which is 1.778. The problem said the initial velocity for M1 was 4. Well, 4 is greater than 1.778. So the answer would be less than, because after the collision, M3 only moves rightward at 1.778. Well, and 1.778 is less than 4, so the answer would be less. Let's do the kinetic energy. Okay. Well, the kinetic energy one is a little more complicated. Okay, slightly. Well, here I wrote KE3, which is 1/2 M3 VF3 squared. But keep in mind that M3 is given, watch where I'm circling on my cursor, or on the screen. M3 is given as 2M2. So that's what I did here. Instead of M3, I rewrote M3 as 2M2. However, M2, as given in the problem, is 2 times M1. So instead of writing M2, I wrote M2 out as 2M1s. So if you did this, if you're watching carefully and if you're keeping up with this, all these substitution, the 1/2 will cancel out one of these 2's in the front, and this will leave you with just 2M1 V3F squared. Well, here I carry down 2M1 VF3 squared, and then I'm just going to plug it in. I don't know what M1 is, so I can't get rid of M1. You can make a hypothetical number if you want, but I don't really care. Okay, so here I'm just going to stick with 2M1 times 1.778 squared. Well, we calculated earlier in this problem right here, where I'm circling back and forth with my cursor, we found that V3F or VF3, however you want to write the subscript, is 1.778. So I'm just going to substitute it in. So V3F is 1.778. I want to square that. So if I square that and times it by 2, it will give me 6.32 M1, whatever M1 is. Well, how do I know if it's less than or greater than? Well, I'm just going to compare it to KE1. KE1 is simply 1/2 M1 times V1 squared. But V1 is given as 4 meters per second. This is the initial velocity of M1. Well, 4 squared is 16. 16 times 1/2 is 8. So really, KE1 is 8 times M1. Well, 8 times M1 is greater than 6.32 M1. So I would say KE3 is less than KE1. So my conclusion for kinetic energy is less than. Let's move on to momentum. Well, to do momentum, all you have to do is set up the statement. Momentum 3 is equal to M3 times VF3. Well, similarly, M3 can be substituted out for 2M2 because that is what it is. But M2 can now be substituted out for 2M1. And then we already know VF3, which is 1.778. So here, 2 times 2 is 4. And then 4 times 1.778 will give you 7.112. And then M1, once again, I don't know what it is, so I'll keep it as M1. But I need to find out what momentum is for initially. Well, initially, the only object moving is M1 to the right. So here's P1, which is M1 times V1I. Well, what's M1? Once again, I don't know, so I'm going to keep it as unknown. What is V1I? Which is 4. So if you simplify this, really I just move the coefficient in the front here. So instead of saying M1 times 4, I can just say it's 4 times M1, so I can make this comparison. Well, in this case, as you notice here, the momentum for the third object is 7.112 times M1. The momentum initially is 4 times M1. So if you think about it, the momentum for the third block, not the system, for the third block, is greater than the momentum initially of the first block. Okay, once again, you're looking at the whole entire system, it'd be different, but here you're just looking at the individual block. All right, other than that, so momentum, it'd be greater than. All right, hopefully you kept up there. Stay nerdy, don't be wired.